Good evening, everyone. Today I'm going to do a demo that is going to hopefully explain aliasing in a little bit more detail and also get you ready for homework 5. This is the continuation of what we started in class today, which was Friday, December 3rd. So I'm going to direct your attention to this section of code right here, and I'm going to run that section, and all it's going to do is create for me a square wave. So you can see I'm using a built-in sampling rate of 1000 Hertz. I don't need to go too much higher than that. I built a time step. I've directed it to go for 10 seconds. Here I build my square wave, and then finally I'm going to plot it. So nice looking square wave. The next thing I'm going to do is I'm going to resample it. Now, in class today, we use the resample command to downsample the signal from our original sampling rate down to some other sampling rate. And in class, I noticed all of a sudden that the resample command was probably doing its own anti-aliasing. And I looked into it and read the documentation, and sure enough, that's exactly what's happening. The built-in MATLAB resample command does anti-aliasing when you downsample, which obviously is important, but for the case, for what we're trying to do in this example, we don't want that anti-aliasing because the whole point of the example is to see what happens when you don't have that anti-aliasing. So I simply I wrote my own version of resample called my resample, which I will post to Blackboard, that will downsample the signal without anti-aliasing it first. So now I'm going to resample my signal just to give you an idea of what's going on here. I'm going to resample it at 2 Hertz, which is about as low as you could get, and I'm going to plot the sampled signal. So in the second trace here, this is what I get when I take my top plot, the continuous time signal, and I sample it at 2 Hertz. So you can see I got a sample here, and then I got 1, 1, 1, 1. So you can see I'm getting 1, -1, 1, -1. In other words, each phase of the cosine of the square wave, I'm getting one sample. You might recall from our class today that when you have a signal that looks like this, a discrete time signal, 1, 0, 1, -1, 1, -1, that's a discrete time cosine with frequency of omega equals pi radians per sample. And that's going to turn out to be pretty important. So here's where the magic part comes. The whole point of sampling is to try to capture a continuous time signal as accurately as possible. So the measure of how well this sampling has worked is that I now need to take my discrete time signal and convert it back into the continuous time. If my sampling was good, then I can expect that the reconstructed signal that I'll get from my discretized samples will look a lot like the original square wave. If my sampling was bad, then something else will happen. So I'm going to direct your attention now to the third section of this code, where I'm going to take so let's see, Y was the downsample. Now I'm going to take Y and I'm going to sample it back up to the original sampling frequency of 1000 Hertz. All right, and I'm going to call that variable Z. And now I can use the built-in MATLAB resample command because it's well, first of all, it's the right command to use, but secondly, when you go from a low frequency to a high frequency, the anti-aliasing doesn't come into effect anymore. So let's execute that line of code, and this is very interesting. Look what happens. So instead of getting a square wave back, I get a sine wave, or a cosine rather. Now at first glance this is a little bit confusing, but if you think about it, it actually kind of makes sense. We learned in class that if you take a cosine at some frequency and you sample it at exactly twice the frequency of the cosine, then you get a discrete time frequency of pi radians per sample. Well, that's exactly the situation that we have here. We have a discrete time signal whose frequency is pi radians per sample. So it stands to reason that if all I gave you was this discrete time sample, the most obvious thing to assume had happened was that those samples came from a cosine. And that's the whole problem with aliasing. Because we didn't capture enough discrete time points, then when we go to try to rebuild our continuous time signal from those discrete time points, we simply don't have enough samples to recreate the square wave. And so instead we got something undesirable in this case, which is a cosine. So we would have been successful when the third trace, the reconstructed signal, looked exactly or a lot like the the trace up here, the continuous time trace. So now what I'd like to do is demonstrate how you can filter this. Sorry, how we can improve the sampling rate. So instead of 2 samples, I'm going to, let's do a few tricks here. So let's double the resample. So instead of 2 downsampling is at 2 hertz, let's try 4 hertz, 8 hertz, and there's 16 hertz. So here you can really see the effects of aliasing. So now every second I'm creating 16 discrete time samples. So those are the samples that you see here in the middle trace. So that's pretty good. On the third trace now, I'm still trying to reconstruct the continuous time signal as best I can from the samples that were taken. So now we've improved a lot. Instead of getting a cosine, now I'm getting some other signal which does look a lot more like the square wave I had originally. Okay, the situation is that if we zoom in, where's the zoom button? Let's zoom in on a single period. Alright, you can see that we get these ripples. And those ripples, believe it or not, are exactly because of aliasing. Okay, it's not for anything else. Because we've taken our square wave and we had all these harmonics that didn't that are now being aliased, that's the effect of the harmonics that we see aliased. All right, so the signal that we're getting back is not, it's sort of like a square wave, but it's not exactly like a square wave. And our whole point was to get something as square wave-like as possible, because that is in fact the signal that we're trying to extract. And so the question becomes, what can we do about this? So the solution is to, and I'm not going to run this piece of code because I want you to put your own filter in here and then see what happens. So I don't, because if I do that, then I'm really giving away the entire homework assignment. So what you're going to do is in the filter design tool, you're going to create yourself a filter. So let me just run through that again with you real quick. I'm going to run FDA tool, which brings up this window. Hopefully you can see it. I'm going to build, just for kicks, let's build a third order filter. The sampling rate of my continuous time signal is just 1,000 hertz. And let's say I want to put the corner frequency at, I don't know, 4 hertz. So let's design the filter. So there's my filter. And now I want to save it. So I'm going to export my filter. I could export it to the workspace, but I prefer to export it actually to a mat file as an object called HD, and I'm going to hit export, and I'm going to call the file filter version 1. Save, and that's it. I can actually close this window now. I don't even need it anymore. So the nice thing now is that when I come over here and load filter version 1, that should load into MATLAB's memory my filter HD, okay? Which you can see the guts of it here, but it doesn't really matter. So now you can apply filter HD. So this is filter H. So the filter, which I'm calling HD, that's my anti-aliasing filter. So look at what's going to happen now. I'm going to take my original continuous time signal X. I'm going to anti-alias it. So here we're going to apply the anti-alias filter. In line 25, I'm now going to use my resample to sample the signal from its original continuous time sampling rate down to the discrete time sampling rate, using sampling rate, in this case 16 hertz or whatever it is. In the homework assignment, I had specified that I wanted you to use 50 hertz here. It turns out that may have been a little bit optimistic. When you sample at 50 hertz for this square wave, there's really not that much energy left after all those harmonics, so you're really not going to see that much aliasing anyway. If you really want to try something exciting, maybe you'll try sampling your signal at something like 10 or 15 hertz. Right? If you try a lower sampling rate, then you'll really see the effect of those of those aliased harmonics a little bit better. So my recommendation is, instead of trying to sample your square wave at 50 Hertz like I instructed on the assignment sheet, try sampling it at something a little bit lower, like 10 or 15 Hertz, in order to see a more impressive effect of the anti-aliasing. So here's the anti-aliasing filter. Now I'm going to take my anti-aliased signal, which is XX, and I'm going to sample at fs Hertz. And then finally, I need to in order to judge how good my sampling was, I'm going to reconstruct my continuous time signal. So reconstruct continuous time signal, if I can spell that properly. And again, the way I do that is I'm going to take my discrete time signal, which was sampled at fs, whatever that frequency happened to be, and I'm going to sample it from lowercase fs back up to uppercase fs, which was in our case 1000 Hertz, or whatever value you choose to put here. Alright, and then finally I just create a time vector and plot the result. So hopefully the result that goes down here will look a lot more like the desired signal, the square wave, than what it looks like when you don't anti-alias first. So hopefully your anti-aliased sampled signal will look a lot nicer when you plot this last section here that I'm not going to plot. So I'll upload this entire set of code to Blackboard right now, and hopefully you'll find that useful in producing your homework 5. So really all I want you to do now is just to create different kinds of filters, mess around with them, see how the signal looks, experiment with changing the corner frequency of your anti-aliasing filter, the number of poles, the type of filter, and see how that affects reconstruction. You also may consider messing around with the sampling rate as well. Alright, so that concludes this example. I hope that clarifies the homework assignment a little bit, and if you have questions, feel free to email. Thanks a lot.